McNair Center was founded in 2014 as a result of the generous gifts of Darla Moore, Anita Zucker, and Marva Smalls. Darla Moore made the initial donation of $5 million to the University of South Carolina with the instructions that the donation be used to start an aerospace program and that it be named after Ronald E. McNair. Anita Zucker matched Darla Moore's donation with another $5 million to fund equipment necessary for the research. Marva Smalls donated $1 million for an endowed scholarship for minority engineering students from the PD region of South Carolina. The McNair Center was named after Ronald E. McNair, a native of Lake City, South Carolina. Ronald E. McNair was an astronaut involved in the tragic Challenger incident. Ronald McNair was planning to come to U of SC as a professor following his final mission. Unfortunately, this did not occur. Here at the McNair Center, our research is primarily industry-focused, with major research contracts through Boeing, NASA, and the U.S. Army. The McNair Center is made up of 4 primary research areas: composites, predictive analytics, drones, and combustion. For the past 20 years, the Center for Predictive Maintenance at the University of South Carolina has been involved in research related to improving maintenance practices using tools such as condition-based maintenance, reliability-centered management, reliability-based asset maintenance, predictive analytics and maintenance, and now digital transformation. CPM's past activities in working with the Department of Defense have produced savings in the tens of millions of dollars, a strong understanding of root causes for better fault diagnosis, and physics-based models for accurate prognosis algorithms and predictions. Since its inception, the Center has strived to undertake new tasks and responsibilities to satisfy the needs of defense aviation. Research activities can be divided into 4 main areas: value engineering analysis, cost-benefit analysis, etc., design, manufacturing, fault, usage, and health-based algorithms, sensor development, testing, and diagnostic or prognostic algorithms, and digital transformation and sustainability. The facility was designed and built to perform experiments on different components for both defense and civilian applications. To address certain types of mechanical failures, the center was focused on the maintenance of the tail rotor drivetrain and main rotor swash plate of the AH-64, as well as the auxiliary power unit for the UH-60. These experiments, through their unique design, allow the center to simulate flight loads experienced by the aircraft. Testing conducted in these stands has led to modifications in military maintenance procedures, resulting in cost savings for the military as well as increased morale and safety. The interdisciplinary team consists of engineering staff, retired military staff, students, and faculty from engineering, business, and public health colleges, with more than $25 million of external funding over the past 10 years. Additionally, McNair Center activities have received national and international recognition. The center has also been involved in implementing virtual reality, VR, and augmented reality, AR, into their maintenance programs. VR is a representation of a physical environment that has visual, auditory, and tactile characteristics. After the environment is complete, the transition is made to create compatibility for either AR or VR. The choice is dependent on application. For industrial applications, AR can be used to overlay condition indicators and descriptions over physical components. VR can be used in training applications for new employees. Both applications represent the vast application base for digital twins and give a strong foundation for the creation of cyber-physical systems. Projects involving AR and VR have addressed training and effective presentation of data. The center continues to build on their history of maintenance research and is now focused on developing and refining a methodology for digital transformation that can be applied to a variety of industries, including aviation, health sciences, automotive, factory, and water treatment. The McNair Center's Digital Transformation Lab is where cutting-edge technology meets real-world use cases. It is home to everything from an Apache AH-64 intermediate gearbox to a premature infant incubator. Although the demonstrations may look different, each one uses the same digital transformation framework developed by the center. Advances in data collection, data visualization, augmented reality, virtual reality, and digital dashboards are present in each demonstration. These technology tools are directed at the end user to provide them a more robust understanding of both the real-time representation and potential future states of the component. Each demonstration has a team of students, both graduate and undergraduate, that work together with industry partners to gain experience and learn valuable skills that prepare them for the workplace. A good example of implementing our digital transformation and Industry 4.0 models is our joint project with the Safran Company. Safran is a leading manufacturer of wire harnesses for commercial aircraft such as the Boeing 787. These wire harnesses are currently made by hand on large wooden form boards. This consumes valuable floor space and time that a current manufacturing company cannot spare. McNair Center students and engineers, along with Safran engineers, created a machine that can manufacture a point-to-point wire harness within tolerance. The machine can automatically measure length and install zip ties on the harness. For components that cannot be automatically installed, a system of lasers will project lines onto the harness to guide an operator when installing a component. This machine is currently being industrialized to be used in Safran's factory in the near future. Another good use case for implementing the digital transformation model is our Apache Intermediate Gearbox. The Intermediate Gearbox demonstration shows how predictive maintenance can be applied at a component level. Traditional approaches use a time between overhaul, or TBO, that states a component must be changed after a certain number of hours. However, this methodology does not account for types of failure that may happen before the TBO. To solve these problems, the center is focused on collecting sensor data such as temperature and vibration at various points on the gearbox. The data is processed, streamed to the cloud, and then presented to different end users. Each end user has a unique screen to view the data in a way that is understandable to them. If action needs to be taken on a component, a manager can start a work order for an engineer and maintenance technician. Once completed, the sensor data will automatically update the health of the component so that everyone can see it in real time. Another very important use case for digital transformation can be found in water desalination plants. A water desalination plant is vital to any civilization, but is especially important to desert countries. The British University in Egypt has, through a joint grant from USAID, partnered with the center to see how digital transformation can be applied to a network of desalination plants across the coast and in the desert of Egypt. A small-scale process control demonstration within McNair's Digital Transformation Lab helps researchers to examine sensor data like flow rate, pressure, and temperature. These data points can help build optimization algorithms at a small scale that can then be applied to a factory scale. Ongoing research includes expanding this demonstration to encompass a system of membranes so that the water salinity and purity can be examined. To address outside engineering applications, we have implemented digital transformation and Industry 4.0 models in the nursing industry. The School of Nursing at the University of South Carolina has done extensive research on the health and well-being of premature infants. Specifically, relationships between core and peripheral temperatures have been found to indicate early signs of hypothermia. As the research continues, the need for data grows, and the center is helping by designing a data acquisition device to collect temperature, pulse, and oxygen data from premature infants. Additionally, the center has created digital dashboards to show the overall health of an infant in an easy-to-read format. Moreover, digital transformation methodologies and Industry 4.0 standards were developed at the McNair Center as training and research tools. A vital tool of digital transformation is data visualization. The center is focused on many forms of this, but augmented and virtual reality are two of the most valuable ones. Each demonstration within the Digital Transformation Lab has a virtual or augmented reality setup to showcase the real-time data and tools for users in each area. Things like training, virtual walkarounds, health indicators, and many others are all developed for internal projects and outside industry partners. In the future, McNair's Digital Transformation Lab will focus on developing a generic framework that can be applied to any use case that may come into the lab. This will provide new students an opportunity to create, test, and share their ideas with faculty, industry sponsors, and other research groups. Additionally, other parts of the McNair Center, such as the Composite Fabrication Lab, have served as a use case, and the tools and technologies developed from that project will be available to students and researchers. Our drone lab is used for the development of autonomous aerial vehicle systems. Research is performed on the development of autonomous flight control algorithms. These algorithms assist the drones with flight stability, autonomous navigation, and tracking. These autonomous systems are used to perform inspection of structures using digital image correlation, sensor installation, and surveying. This lab includes a 25-foot by 20-foot by 20-foot flying cage with 16 camera OptiTrack motion capture system. The lab features a fleet of 13 commercial drones along with other small autonomous vehicles. Developments within this lab will assist with increasing the safety of the airspace, improve safety of structures, and reduced costs of commercial drone operation. Future work includes development of modular, fully autonomous unmanned rotorcraft. The manufacturing sector is currently reinventing itself by embracing the opportunities offered by digital transformation, industrial internet, cognitive automation, and artificial intelligence. In the McNair Future Factory Lab, researchers are looking to pursue the potential convergence of cyber architectures, physical manufacturing processes, and control intelligence. In the Future Factory's manufacturing cell, you can see a demonstration of cyber-physical systems for a 5-robot assembly line. Collaborative robots from Yaskawa Motomen are controlled by a safety-enabled Siemens PLC system. Industrial sensors and visual systems are embedded as smart devices to monitor the process indicators and device health states during the machine operations. The cyber infrastructure is constructed based on Siemens Industrial Product Lifecycle Management software solutions, which create a high-fidelity, simulation-based digital twin for the physical assembly line. The automation signals are synchronized and exchanged between PLC and the cyber systems. The researchers are also pursuing the deployable industrial AI connecting the cyber-physical system. The inspection results, inferenced from multiple sources such as industrial sensors, inspection cameras, FLIR thermal camera, and the Unmanned drone are synchronized in the control loop. The state-of-the-art computer vision, neural networks, and reinforced learning are supporting the autonomous decision-making by artificial intelligence in the cyber-physical system. Also included in the Future Factories Lab, you can see an industrial implementation. We collaborate with a Colombia-based pharmaceutical company, Nephron Pharmaceuticals, to revolutionize their manual production line with robotic systems. The researchers have accomplished a reliable engineering solution to automate the sequence of syringe delivery, drug filling, and product capping. This significantly improves the process sterility, precision, and efficiency required by Nephron Pharmaceuticals. Moreover, programming physical robots with developed virtual commissioning platform is precise and user-friendly, which do not require a robotics engineer to operate them. Future work includes the research on interoperability of future manufacturing. The Future Factory is doing a significant amount of work towards web-based cyber manufacturing platforms to enable the communications and collaborations among the machines, between humans and machines, and among humans. Our largest piece of research equipment is the Lynx Automated Fiber Placement Machine by Ingersoll Machine Tools. Ingersoll Machine Tools is one of our industrial partners here at the McNair Center. This gantry-style fiber placement machine is the same style you would find in any industry where they manufacture large composite structures, including the Boeing 787, F-35 Joint Strike Fighter, Gulfstream G650, and large wind turbine blades. We are the only research facility with this style AFP machine in dedicated research. The Lynx is used to lay up quarter-inch wide toes of carbon fiber across tools for additive manufacturing of parts. The toes are made of unidirectional carbon fiber. In automated manufacturing, the unidirectional materials are preferred for ease of use and improved material laydown rates. Woven materials are typically used in hand layup processes. The system has 7 axes control: X, Y, Z, 3 rotary axes, and a rotary positioner. With this system, we can use a variety of tools, including flat, double curved, and cylindrical. Our system can either use IR heating or the Hum-3 intelligent heating system from Heraeus. The system is capable of laying up composite materials at speeds of up to 50 meters per minute on an optimized part. The Lynx can be used for manufacturing of parts using thermoset, dry fiber, and thermoplastic materials with either carbon fiber or glass fiber. Toes are pre-impregnated with either thermoset or thermoplastic matrix materials. Dry fiber toes contain a thin veil of thermoplastic on the surface for adhesion. The preform is then infused with the resin in the oven after fiber placement. Our research is focused on the process development. This mostly concerns new methods for manufacturing. You can see some examples of unique laminate types which we have developed, including locally reinforced panels, quasi-woven panels, and fiber steering. Fiber steering involves development of curved fiber paths to increase either strength or stiffness. We also do a significant amount of work in the realm of thermoplastic composite manufacturing. Our research areas include thermoplastic fiber placement, induction welding, 3D printing, and friction stir welding. If you are unfamiliar with the difference between thermoset and thermoplastic polymered materials, the basic difference is the ability to be reformed after initial part production. Thermoset polymer materials undergo a chemical reaction during curing which causes cross-linking between the polymer chains. The cross-linking is formed by covalent bonds which are stronger than the bonds between the atoms in a molecular chain. If you try to heat the materials to melt them, you will destroy the polymer chains before you are able to melt the material. Thermoplastics are made up of discrete polymer chains, which can be melted to allow for novel assembly techniques including induction welding and friction stir welding. Thermoplastic fiber placement is achieved using the HUM-3 system on the Lynx AFP machine. Currently, we have a 6 kilowatt HUM-3 system, which allows us to lay up PAEK at about 1 meter per minute. Soon, through our partnership with Arrayas, we will be installing a 30 kilowatt HUM-3 system, which will allow us to lay up PAEK at approximately 20 meters per minute. We have also done thermoplastic AFP research with PEI, PPS, and PEKK. The McNair Center is also involved in the development of automated inspection methods for AFP. We use a system by Ingersoll Machine Tools called AXIS, the Automated Composite Structure Inspection System. AXIS uses laser profilometers to scan the surface of a part to create images of difficult to visually inspect materials. AXIS then analyzes these images and correlates them to a database of known defect images. Once the defects are identified, an assembly guidance later outlines the defects as they are verified using a tablet or smartwatch. AXIS allows for manufacturers to obtain quantifiable inspection and repair data for composite parts. Plasma treatment research is conducted in the McNair Center to develop improved methods for production of adhesive bonds in composite structures. We have an atmospheric plasma generation system by PlasmaTreat. This system used high-frequency power and compressed gas to eject plasma from the workhead. The plasma is used to remove contaminants on joint interfaces. This system provides a quantifiable cleaning of the surface. This process provides a more reliable method for joint preparation. The goal is to be able to produce reliability high enough that adhesive joining can be used in primary structures of aircraft without mechanical fasteners. Future work includes advancement of thermoplastic fiber placement techniques, development and testing of out-of-autoclave composite manufacturing techniques, development of automated inspection methods and predictive models for defect prevention, development of tools for rapid analysis of structural effects of defects. In this lab, we develop finite element tools for optimization of process and design parameters. Some of the things we are working on are aircraft optimization, laminate optimization, and induction welding design tools. One of our other major research areas is in the field of multidisciplinary design optimization, MDO for short. MDO uses algorithms to optimize parts for specific variables, using governing equations and boundary conditions. We use MDO in two main areas, aircraft design and laminate design. In aircraft design, we use a software we developed to optimize airfoil shape for a parameter of choice. This could be fuel economy, top speed, lift, etc. We input the initial airfoil shape into an optimization environment and choose the optimization parameter. The software then runs a computational fluid dynamics analysis of multiple iterations of the airfoil shape. It then outputs the optimized shape of the airfoil. The final airfoil shape can then be tested in a wind tunnel to verify the calculations. This method allows for a large amount of designs to be tested in a relatively short amount of time, significantly reducing the design time. We have completed Phase 1 development of a military drone called the Dash-X using this software. This work was done in collaboration with one of our partners, VX Aerospace and Northrop Grumman. In laminate design, we use MDO for optimization of fiber steering laminates. We use a software we developed in-house called ShapeTerra to optimize the fiber paths. We started by defining the part geometry and loading characteristics. The software then creates curved fiber paths based on the optimization desired, which could be stiffness or strength. The software then outputs the fiber paths for a manufacturer using the AFP machine. This lab focuses on the characterization of process structure property relationships of additively manufactured advanced composite materials. This is accomplished through integration and manufacturing, materials, and multi-scale mechanics. This method allows for rapid characterization of material properties and design applications of advanced composite materials. The lab features a fiber and yarn testing machine with high-performance computing clusters. Additional additive manufacturing equipment is being added, including a PolyJet 3D printer. Current research includes characterization of advanced high-friction ballistic fibers, determination of fundamental mechanisms governing tensile strength in carbon fibers, investigation of damage-tolerant composites, computational modeling of dynamic, high-energy impact responsive composites, and multi-scale additive manufacturing techniques for impact resistance. Future work includes fundamental and applied research on novel composite architectures for impact resistance and damage tolerance with aerospace and armor applications. The McNair Center has large curing equipment to match the part capabilities of the Lynx AFP. The McNair Center has a composite curing oven from Wisconsin Oven. The oven has a maximum interior working space of 6 feet by 10 feet by 5 feet. The oven is capable of processing engineering thermoplastic materials at temperatures of up to 800 degrees Fahrenheit. This oven is also equipped with an advanced infusion system for use with elevated temperature infusions of toughened epoxy resins. The McNair Center also has a composite processing autoclave by Bondtech. The autoclave has a maximum interior working space of 6 feet by 10 feet. The autoclave is capable of processing engineering thermoplastic materials at a temperature of up to 800 degrees Fahrenheit and pressures of up to 250 psi. The autoclave and oven size allow us to make parts that are of relevant size to the aerospace industry, for instance, winglets for business jets. The McNair Center also has a compression molding machine from Wabash MPI. The compression molding machine has 24-inch by 24-inch platens with 10 inches of daylight opening. The compression molding machine features programmable heating and cooling rates. It utilizes electric heating and water cooling. The compression molding machine can process engineering thermoplastics at up to 800 degrees Fahrenheit with 50 tons of clamping force. We also have facilities for vacuum bagging and vacuum-assisted resin transfer molding. These facilities include a CNC fabric cutting table by Gerber Technologies and a high-quality vacuum infusion cart from Vac Mobiles. In our Vartum lab, we also have a fume hood, which we use for impregnation of carbon fibers for our 3D printing filament. These filaments are later used in our 3D printing lab for development of continuous filament 3D printing. The thermoplastic welding cell, located here at the McNair Center, utilizes high-frequency induction welding technology to assemble parts without fasteners. The induction welding technology allows manufacturers to reduce overall weight and recurring cost associated with fasteners and adhesives through fastener-free assembly. The research entails induction welding, equipment design, process parameter development, in situ monitoring of the welding process, and characterization of welded joints. Our induction welding cell offers 2 different induction heaters from Ambrell. One is a 10 kilowatt easy heat system, and the other is a 45 kilowatt echo heat system. The induction heaters take normal 60 Hz power and increase the frequency up to about 300 kHz. This rapidly oscillating current creates a strong magnetic field around the coil. When the magnetic field is brought in close proximity to a conductive material, it causes rapid heating of the material. Carbon fiber is very conductive, so it heats up rapidly. When the thermoplastic materials are heated up under pressure, a weld is performed. This weld is sufficiently strong to be used in primary structures of aircraft. Pressure can be applied using hard tooling or vacuum. We have also developed a method for process monitoring and control using fiber optics. The method uses an optical fiber to measure temperatures across the weld zone to ensure that proper heating is attained. We also have mechanical testing capabilities within the McNair Center. These include static testing using our electromechanical testing frame for up to 50 kilonewtons, or dynamic testing using our servo-hydraulic test frame for up to 100 kilonewtons. Our research activities also include the design and development of continuous filament 3D printing equipment, process parameters, and feedstock materials. This has been commercialized with our partner Ingersoll Machine Tools and Masterprint Continuous Filament. This process is used to produce parts which are selectively reinforced with carbon fibers. These manufacturing and parameter development research is supported by an extensive background in computational modeling dedicated to these and other composite manufacturing needs. The future of this research is to continue improving manufacturing process for thermoplastic composites. One of the most recent additions is the metal 3D printing capability. This lab features versatile laser powder bed infusion additive manufacturing machines, a Conity MIDI. It equips a high-power 1 kilowatt laser with controlled chamber environment, including a unique vacuum option. This system is capable of processing a wide range of engineering materials, such as aluminum alloys, stainless steel, refractory material, and nickel-based superalloys. The process is particularly well suited for customizing materials' properties and use with materials that are difficult to machine or parts that may have geometries that cannot be produced using traditional manufacturing methods. In addition, the lab also specializes in multi-scale physics-based modeling to understand and predict the physical phenomenon and material behaviors during and after the process. The lab currently focuses on both process and materials innovations, assisted by sensors and multi-scale computational models, to achieve customized microstructures and materials properties for engineering materials. Three major activities include a smart additive manufacturing system enabled by online sensors and computational modeling to adapt instabilities during the printing, process modification to synthesize materials with highly customized microstructures and zero defects, and advanced solidification microstructure modeling enabled by hybrid parallel computing. The lab continues working on the full integration of online sensor, multi-scale computational modeling capabilities, and advanced data science, including artificial intelligence to push the boundaries of materials engineering in additive manufacturing. We are also home to a Combustion Lab, which supports combustion research needs for aviation and aerospace. This is our Combustion Research Lab. In this lab, we work on the characterization of the combustion of fuels. Research in this lab is used to optimize fuel usage for improved energy production efficiency and reduced emissions. Recent research directions include developing physics-based tools for rapid fuel property characterization and optimization for advanced gas turbine, augmenter, and ramjet propulsion applications. Petroleum-derived and renewable jet fuel property effects on commercial aircraft engine design, performance, and emissions. High-fidelity, compact chemical kinetic physical models for computational engineering design. Relating internal combustion engine combustion emissions to physical chemical properties of natural gas, industrial byproduct gases, liquids, heavy fuel oils, and crudes, real-time fuel property measurements, onboard modifications for optimizing the fuel energy conversion process to enhance performance emissions characteristics, and fast actuating high-density microplasma devices. Emerging research interests include characterization of liquid spray atomization vaporization properties on carbon deposit formation and energy conversion devices, extreme high-pressure supercritical combustion in air components and carbon dioxide chemical product fuel production from municipal industrial wastes, engine lubricant property optimization, and marine application interests in heavy fuel and oil desulfurization. Serving our operation, we have an in-house fabrication facility to design and fabricate experimental setups, prototypes, as well as other research-specialized tools. In our fabrication shop, you will find all the tools necessary to support our research. Large stand-up tools like a bandsaw, sander, drill press, and bench grinder, sheet metal tools like a press, brake, and shear, along with the Miller Multimatic welder for stick, MIG, and TIG welding. We also have a Haas VF550 with TR310 trunnion for CNC milling of parts to make tools and fixtures. The mill is capable of 3+2 machining and has a maximum part size of 50 inches by 24 inches by 25 inches. The mill is used for preparing composite parts for testing. Our thermoset composite storage freezer is located in the suite and is used to store our composite prepregs at -15 degrees Fahrenheit. In conclusion, as you have seen in this video, the 35,000 square feet of the McNair Aerospace Research Center is home to more than 30 faculty members and more than 150 students and scientists from across the University of South Carolina campus system. The center covers areas of research, development, and hands-on methodologies in design, manufacturing, testing, sensing, characterization, automation and cyber manufacturing, predictive analytics and maintenance, digital transformation, digital twins, machine learning, Industry 4.0, and many other methodologies for the digital age. With compliments from all of us at the McNair Aerospace Research and Innovation Center, Dr. Abdel Bayoumi, Director. For more information, please visit us at sc.edu/McNair.